and various forecasting workshops around the world. Welcome, Mitchell.
Okay, hey everyone. Today I'm going to talk a little bit about statistical computations with distributions. And this is a tools package, which I hope that you can use to make working with distributions a little bit easier, especially if you're writing some models and making predictions from a model or doing statistical tests with your package development. I think this could be quite useful for you. So distributions in R leave a lot to be desired, and as a statistical programming language, you would really hope that it can do distributions quite well, compute densities, cumulative distribution functions, sample from distributions, etc. But you'll see hopefully shortly, I can convince you that there's a lot of opportunity for improvement. So there's a few common uses that you might encounter with distributions in R. The first of which is to make predictions from models, of course. You can also simulate data and do some studies with that. Often you'll encounter distributions with hypothesis testing, but often you just look at the p-value, not seeing the whole story perhaps. And also I use this a lot for teaching statistics as well. So there's actually a lot of packages on CRAN which achieve some form of distributional analysis. There's in fact over 300 packages, and I'm just going to talk about the one that I've made. But they're all designed around, there's a few that try to design distributions in R a little bit better, but most of the packages are unnecessarily complex, and this inherits a lot of the functional design of using the PDQR functions from stats. So there's two main problems that I can identify with the existing distribution functions. The first of which is the functions themselves and how they're designed. The names and the arguments can be a bit confusing. And secondly, the output that you get from models and predictions, and statistical tests, don't really highlight the uncertain distributional nature of that test. So could we potentially have a better way of doing this? And improved designs, I believe, can overcome these issues. So if you're unfamiliar, I imagine everyone is familiar with this, the PDQR functions, the P stands for probability, and you might better know this as the CDF, the cumulative distribution function, and I often confuse the P for the density, the PDF. I think that's a very natural, because I think PDF and CDF, I often get confused there. But D is actually for density, and density is a function that already exists in R. I use it on a sample, of course, but density cannot work with distributions. There's some inconsistency in how you use these functions. You've also got Q for quantiles. There's also a quantile function, doesn't get used for distributions, and R for generating some random samples from that distribution. And with some extension packages, they also go into finding moments of distributions. So you might find M functions of these as well. And often these aren't the only four things that you want to do with a distribution. So it can be a bit limited in that respect. So the PDQR functions follow this general form, and it's a bit of a conjunction of three main elements. You've got the operation that you're doing, say you're calculating the quantile or generating data, but that argument is split inside the function as well. So you've got to specify both at the start in the name of the function and inside the arguments of that function as well. Secondly is the shape of the distribution, and tightly coupled with that is of course, the parameters of that distribution. And this causes a bit of a naming conflict with the arguments of the function, because both the arguments for the operation and the parameters of the distribution share the same namespace, and that can cause some design problems. So for example, if I was calculating a density at 0.5 of a normal distribution, I need to know quite a lot of things about how to use R and these. And for first-time learners in statistics, just thinking about what a density is hard enough. So we have the type of operation, P for density, confusing, and the position of the density, Q equals 0.5. That's the quantile. And lastly, of course, the parameters of the distribution, and I get a number out from this. If I wanted to calculate a quantile, I switch out the P for a Q and the Q for a P. They're not very descriptive names of what you're doing. So this causes some name conflicts, even in the function names themselves. If you ever created a data frame and called it df or dt, you might want to reconsider because that will conflict. It doesn't cause many problems, but it conflicts with the definitions of the functions that already exist. So it's bad practice. Probably the worst offender of these distributions is the way that they recycle arguments. So the PDQR functions are nicely vectorized, meaning you can calculate a lot of things from a lot of distributions all at once, and it's implemented quite low down in C or C++, and so it's very fast as well. How exactly these functions vectorize things can cause a lot of problems. So you may have seen something like this. We calculate a 95% interval, so 0.025 and 975 quantiles, from a normal 1 variance 9 distribution, mean one. And that works. But what if I wanted to calculate from multiple distributions? So I've got 4 different normals here, and I use the same probabilities for my quantiles, those 4 distributions, but I don't get 4 intervals as a result. I have the first quantile matching the first distribution, the second quantile matching the second distribution, and then it recycles. So the first attribute, the first parameter for the quantile is matching the third and the fourth to the fourth, second to the fourth. And this is a really surprising recycling behavior. You essentially need to replicate these things appropriately so that it does the recycling the way you expect. And quite often I see the students, they just see an output, they don't see an error from this, and they happily continue without being any wiser about the underlying problem for this. So these sorts of silent errors are perhaps the worst you can encounter in design. So a well-designed function, what do we want to improve for this? We need clear and descriptive function names that describe what they're doing. We want to clearly and well define the parameters of that distribution, and also the arguments for the operation you're doing, say density or quantile. You shouldn't need to duplicate code, so replicate the vectors for you, or you'll find that if you wanted to calculate the intervals a bit easier, often I just do them in 2 separate qnorm calls. So that I don't recycle the arguments, then I have to duplicate the parameters of the distribution. So I want to avoid that as well. Okay, and lastly, it needs to be predictable. So this recycling rule needs to be improved. So to improve upon this, we want to avoid all the problems that I've just talked about, and also these improvements will hopefully allow us to get better outputs from our distribution. So if I'm making a prediction, for example, here is an LM model, just predicting the penguin bill lengths using various attributes of the penguins. And if I use predict, I don't get distributions. But this prediction task is naturally uncertain. We don't know exactly, well, of course this is in the data, but from the model, we don't have an exact idea of exactly the size of this bill depth or bill length. So uncertainty is really important for making good decisions, but it's really de-emphasized by a lot of the model outputs that you usually use. To get the model outputs, you need to find an extra argument for LM, and this varies from model to model, but the one for LM is se.fit equals true, so give me the standard errors. And it gives you a little bit more than just standard errors. It gives you the degrees of freedom and the residual scale, and you need to understand how to use these to parameterize the distribution. You need to know what that distribution is in the first place. So it's not very helpful, especially if you're less familiar with statistics. So it gives you a bit extra, but still doesn't really give you the probability distribution. It doesn't tell you the shape, you just have to know that, which might not be the worst thing. But maybe I write some code to calculate those 95% intervals, and I want to do this for maybe plotting. We use geom-smooth a lot to also conveniently create stuff like this. And it looks okay. I do a QT for quantiles of the t distribution. I set the degrees of freedom, the point forecast, the standard errors, and I get my intervals. So that requires a bit of code duplication and a bit of understanding of not just how to parameterize the distribution, but how to modify it with scale and location. But I kind of lied. This isn't prediction intervals. These are actually confidence intervals. What's the difference? That requires even more understanding of what's going on. And I just said predict. I might not know the difference, and I see this commonly mistaken, confidence versus prediction intervals to happen. So did you notice that? Probably not. I just wrote some reasonable looking distributions and made them myself. Here is the actual code for prediction intervals. I need to square root the standard error, add on the residual scale, and square root again. because they're all invariances rather than standard errors. And I think that's right, I'm not sure. But it would be much nicer if instead of giving me the ingredients to make a distribution, the model just gave me the distribution. Then there would be no ambiguity for how to get the intervals or quantiles from this. So hopefully by improving distributions, we can improve our modeling and the outputs our model is designed to directly help us and give us the output we want. So hopefully I can motivate some better distributions for R with the distributional package. And this package uses vectorization, not just on the distributions, but also on the parameters separately as a design alternative. So by separating distributions and how you create them as a first step, and then using the distributions, we reduce a lot of duplication of parameterizing distributions. We also reduce the risk of making mistakes when you're copying and pasting code, but also constructing these distributions. The function naming, of course, can be improved as well. Statistical computing works for all functions, all distributions using the same function. So we can get back density and quantile without needing the P and the Q. I'm making a mistake again, P and the Q. And lastly, we really need to improve the recycling rules. So we'll keep an eye on that as well. Here's how you create a distribution with the distributional package. Say I'm creating a normal distribution, the same that I described before. I can use dist_normal, so it uses the auto-completing name convention prefixed with dist. And there's 21 different continuous distributions, 9 different discrete distributions, and in fact, any PDQR function can be wrapped up using distwrap. So this works for many of the distributions that you're probably working with today. And there's also some miscellaneous types of distributions, such as degenerate, sampled empirical distributions, and if you've just got the quantiles, you can use them. Now, this is inherently vectorized. If you've seen vectors packages before, you may be familiar with this print output. Creating those same 4 distributions from before, I get 4 distributions neatly formatted in a vector. So this contains both the shape and the parameters, and we can use it to calculate statistics. We can even mix distributions, so I've got gamma distributions added into my normal distributions here, and we can compute on those simultaneously. Because they're vectorized, they also work with tibbles. So this is really nice if you're returning an augment of your data set. You can add a distribution of fitted values rather than just the fits themselves. And this is what I use quite a lot in the Fable package for when I produce forecasts. So there's no risk of misspecifying the distribution when you produce fables because the forecasts are entirely contained in this normal column. And that's what we use for any calculations and plotting and subsequent writing out of this, for example. So here's the translation for PDQR. We have the CDF function for the probability of the distribution. The D is now density for the PDF. That's because it already exists in R, and unfortunately PDF, the portable document format, is a bit of a conflict there. Q for quantile, so you can reuse existing things, existing tools that you would use for samples. We've used the quantile function before. You might have used generate when doing modeling. That also works for distributions in this design. So with this normal distribution, I calculate the quantiles at 95% symmetric. And you can see I no longer have this recycling problem. I have, for each distribution, I get 2 different quantiles for the lower and the upper bound. Or there's a simpler approach. We've got a built-in high-load function for calculating intervals, and it has a nice thing about it. You can also do a lot more than just PDQR. You might like to calculate log likelihood. If you've got bimodal distributions, HDRs are useful. Means, variances, moments, units, kurtosis. We can add to this as we go. Now, vectorization is a really touchy topic here with distributions, and it's something that I've spent quite a bit of time on. So there's 2 different ways of vectorizing distributions because there's 2 things that you might vectorize over. The first is that you might vectorize over the distribution. The second, you might vectorize over the parameters, the arguments of the operation, the quantile at what probability, for example. So this is represented in the same argument depending on if you use a vector or a list, or equivalently a matrix for multivariate distributions, or if you want nicer tidyverse integration, data frames and tables work as equivalent to lists. So the vector approach is what I was showing you on the previous page. This is a much simpler approach, but it's not as flexible. Whereas the list approach allows you to do anything that you currently do with PDQR functions, but with a better, more safe design. Here's the vector approach. So I've created 3 different distributions, a normal, beta, and gamma distribution. And I'm calculating the density at a specific location. And I get 3 numbers in a vector. So this is quite natural for mutating a column of the data frame, for example. But if I produce a couple of vectors, it gets recycled first with the distribution. So you can see the first distribution, second, and third. And then within that layer, we get each of the densities. Here it is in a mutate approach, so it works quite well for a single quantile, or density, I should say. But it's a bit tricky if you're doing more than one density at the same time. You can, of course, spread this across multiple arguments, but we have this nested list structure that you might need to unpack. You might need to identify which element corresponds to which probability. The list approach, on the other hand, is a bit more complex, but it's more flexible as well. So you get a bit of a trade-off there. In this case, I name the list. So I say the D1 column is going to be 0.65, and then it will calculate first by at of the density. So I've got the D1 column, and then within D1, I have each of my distributions. So it's doing the arguments first, and then the distributions, rather than the vector approach does the other way around. Now, this works a lot better if you're doing multiple densities, if you're doing 0.65 and 0.9, because now across columns, you have a data frame. So you can pull out exactly what it is for the distributions. This works really well. I should talk about vectorization with this as well. If you really wanted to do what PDQR does and vectorize both the arguments of the operation and the parameters of the distribution, you can specify the same length at positions for the density with the same length of distributions. But generally you don't want to do that, and that's why it's a bit trickier to do here. And if you try to recycle something that isn't compatible, if it's not length 1 or length n, the Erlang tidyverse standards, you just get an error, rather than recycling and trying to do something that PDQR does. In a data frame, the list approach works really well. So here I'm mutating the density at 0.65, and I get an extra column. But if I do multiple columns this time, mutate actually automatically unpacks if you don't give it a name. If you give it a name, it'll be a nested table structure, which also is quite nice. Now, there's also some tools, because we've got distributions stored as objects in a vector now, we can also use those distributions to create other distributions, which is quite cumbersome to do with the functional approach. So I've got distinflated for doing any sort of inflated distribution. You also can truncate any distribution. What I like to do a lot with my forecasting is transform the distribution for non-negativity or various multiplicative patterns to simplify them through my workshop yesterday. So we use this transform for that. And we might also mix distributions together. So here's what some transformations might look like. I add 2 to a distribution, and it takes a shortcut. It just changes the underlying distribution if it knows how to do that. If I multiply that distribution by a scalar, you can see you get what you would expect from a normal. And even if I take the exponential, I get a log norm. So it's able to change the shape as well, if it's aware of these relationships. If it's not aware of the relationships, it will fall back to the default transform distribution. So you can see I've squared the normal distribution here, and I get a transformed normal distribution. It doesn't quite know what the shape is. It might have a name. It doesn't know about that name. But it can calculate all the statistics you might like using numerical methods. And where possible, it will use symbolic differentiation to make this very accurate. So the square root will symbolically differentiate and give you the appropriate mean, variance, CDF, whatever you like. Last thing is the wonderful ggdist package by Matthew K. And we kind of made these packages at similar times. We were both on the newbies channel for submitting packages, and we're like, we should work together on this. So it now works directly with distributional vectors, which is perfect for if you're using distribution vectors in a data frame. So here I've got my dist column with a few different distributions. You can also see the mixture distribution on the line 6 there. And then I can use ggdist with a specific statistic. There's lots of different options for this. And the dist aesthetic is going to be my distribution vector. So this is a really powerful tool, not just for teaching, but also for looking at your forecasts, your predictions from a model. You can also do intervals from this. There's quite a lot of options for that. So some key ideas, just be careful with vectorization if you have to use PDQR, but maybe you can consider using this package for your research, your analysis, and your packages. It's also nice for teaching if you're teaching. And there's quite a lot of extra work to do. I would like to add more distributions. If you care about a distribution, come help me, contribute. And convolutions and moments are on the way. And of course, I need a hex sticker. Uncertainty shouldn't be an afterthought in statistical programming. So making easier statistics will produce more reliable, accurate results. And this was made using the vectors package. It wouldn't be possible without that. So thank you, everybody. And I hope you learned something. I'll open questions.